Deep beneath the Swedish countryside, a groundbreaking scientific project is reshaping the future of research. Picture a microscope so powerful it can unveil details smaller than an atom, tools that could revolutionize materials, medicines, and tackle humanity's greatest challenges. What does it take to build such a machine, and why are 13 nations investing billions? How do you accelerate protons to near light speed and unleash invisible particles to peer inside matter? This is the story of international collaboration, cutting-edge physics, and a $3 billion investment that could transform everything from energy to health. The power of neutrons. At the heart of this enormous scientific endeavor lies the humble neutron, a tiny, neutral subatomic particle with extraordinary investigative power. Unlike electrons or protons, neutrons can penetrate deep inside materials without causing damage, acting like microscopic probes that reveal the hidden structure of things at an atomic level. This capability allows scientists to explore how atoms are arranged and how materials behave, unlocking insights that are impossible to gain from the surface alone. It's this unique characteristic that makes neutrons invaluable for advancing fields as diverse as energy, medicine, and materials science. However, neutrons don't come free or easily. These particles exist only inside atomic nuclei, and to coax them out, you need a clever process involving another particle. The proton. By firing high-energy protons at a special target material, tiny pieces of the target's atoms are knocked loose, releasing neutrons in the process. This is a controlled nuclear reaction, one that's powerful yet managed carefully enough to avoid the chain reactions seen in nuclear reactors. Scientists call this method spallation, likening it to smashing a piece of concrete with a sledgehammer and collecting the fragments that fly off. This neutron production forms the core challenge and triumph of the facility, generating a practically limitless supply of neutrons for researchers to wield. It's this quest for neutrons that drives the incredible engineering behind the entire project, setting the stage for discoveries that could revolutionize technology and medicine. As we explore further, you'll see how this process unfolds inside the mammoth machines at the European Spallation Source and why it demands nothing less than international cooperation and cutting-edge design. The journey to harnessing these elusive particles begins deep within an underground tunnel where one of the world's most powerful accelerators stretches like a metallic serpent. The accelerator tunnel. This tunnel is home to a particle accelerator that propels protons to an astounding 96% of the speed of light, an engineering feat that requires extraordinary precision and power. The protons begin their journey in an ion source, where beams are generated and then pushed through a vacuum pipe by a sequence of magnets and radio frequency devices. These magnets serve a crucial role, focusing the beam tightly as it races down the tunnel, ensuring the protons don't scatter or lose energy. Maintaining this level of control over particles moving so fast is one of the most complex challenges facing the engineers and scientists. The accelerator itself is a linear machine, quite different from the famous ring-shaped Large Hadron Collider at CERN. Instead of cycling particles around a circle, this system accelerates them in a straight line toward a target several hundred meters away. At 5 megawatts, the accelerator will be over twice as powerful as similar facilities currently operating elsewhere, positioning it as the most intense neutron source in the world when fully operational. Such power not only requires state-of-the-art technology, but also a strong commitment to safety, with strict systems in place to prevent any human presence in the tunnel during operation due to radiation risks. Installation of this colossal accelerator began in 2017, piece by piece, with commissioning ongoing into 2025 and beyond. It is a testament to decades of expertise flowing from scientists and engineers worldwide, combining to create a machine capable of fueling the entire neutron production process. But the proton beam is just the first act. The true spectacle emerges where these high-speed protons meet their destiny in the target wheel, and the unleashing of neutrons begins. Once accelerated, the protons slam into a heavily shielded target that turns their kinetic energy into a torrent of neutrons, an extraordinary mechanical and scientific dance housed in one of the most carefully engineered parts of the entire facility. The target wheel and monolith. At the end of the accelerator tunnel lies the tungsten target wheel, a 5-ton stainless steel disc with multiple segments. Spinning at 23.3 revolutions per minute, it ejects vast numbers of neutrons as protons strike it. Tungsten's density and neutron-rich properties make it perfect for this task, ensuring efficient neutron release and durability under extreme conditions. Precision is critical, as each proton must hit a segment exactly once per rotation, requiring tight coordination between systems. Surrounding the wheel is the monolith, a massive 6,000-ton chamber that shields against intense radiation from the nuclear reactions. Its construction was an engineering feat, with stainless steel blocks assembled to exact tolerances. Layers of concrete and iron ore absorb radiation and withstand mechanical stress. Inside the active cell, radioactive components are handled remotely by robotic arms, ensuring safety while allowing maintenance and part replacement. The target wheel and monolith represent the balance of power and precision at the heart of the facility, with neutrons soon traveling through instruments to unlock the secrets of matter. Behind all this technology is a collaboration of nations pooling resources and expertise, each playing a vital part in making the unimaginable possible. And if you're curious about how countries unite for such groundbreaking projects, make sure to like and subscribe for more. International collaboration. The European Spallation Source, ESS, is made possible through unprecedented international collaboration. 13 nations have pooled their resources, knowledge, and manpower to create this massive project. Sweden and Denmark provide nearly half of the 3 billion euros in funding, while other countries contribute specialized equipment, components, and expertise through an in-kind model instead of direct funding. This partnership eases the financial and technical burden, creating a network of over 100 institutions and 40 in-kind partners across Europe. By focusing on their strengths, whether in engineering, scientific instruments, or software, countries accelerate progress and innovation without duplicating efforts. Beyond the laboratory, this collaboration fosters a community of researchers, engineers, and students working toward common goals that promise to revolutionize industries and improve lives. The scale of this cooperation shows how investing in big science benefits economies and societies. At the heart of it all, neutrons generated by the ESS are used to uncover the universe's smallest secrets. These instruments are where theory meets practice, where science unfolds in real time, and where discoveries take shape across countless fields. Scientific instruments and experiments. Once released from the target, neutrons travel along specialized beamlines to an array of scientific instruments, each designed to analyze specific material properties by measuring how neutrons scatter when they pass through samples. Instruments like Odin, Magic, Dream, and Beam focus on everything from imaging internal structures to investigating magnetic or chemical behaviors with unprecedented precision. Researchers place samples, ranging from superconductors to fragile artifacts, into these instruments, subjecting them to controlled environments, often at cryogenic or vacuum conditions. The scattered neutrons provide detailed information about the atomic structure, which is captured by detectors and analyzed against theoretical models to uncover material secrets. Neutron-based analysis is non-destructive, offering a major advantage over other methods by preserving delicate samples. This facility enables breakthroughs in energy solutions, stronger materials, advanced pharmaceuticals, and quantum computing. Thousands of researchers from Europe and beyond utilize this cutting-edge technology annually to conduct experiments that have far-reaching implications, from improving MRI magnets to advancing battery technology. The facility stands as a hub for innovation, where every neutron helps unlock transformative insights about our world. Through the power of shared vision and varied expertise, what began as an idea has become a global hub for scientific revolution, and its impact is only just beginning. Environmental integration and future impact. The European Spallation Source, ESS, is not only a scientific marvel but also a model of environmental integration. Designed to blend seamlessly into the Swedish countryside, the facility avoids imposing structures, with wild grasses and native vegetation surrounding it. The unique sombrero roof allows wind and snow to pass through, reducing environmental impact. ESS also prioritizes sustainability by repurposing heat from its accelerator systems to warm 20,000 residents in nearby Lund, turning waste into a valuable community resource. This focus on environmental responsibility reflects a growing trend in infrastructure projects to minimize ecological footprints while supporting high-tech advancements. While its full impact is still unfolding, ESS has the potential to drive global innovations in materials science, medicine, and energy. Its research could lead to better cancer treatments, more efficient batteries, and breakthroughs in computing and renewable energy. As it nears completion, ESS stands as a symbol of international cooperation, visionary engineering, and a brighter future, with its promise of transformative discoveries benefiting science and humanity alike. From splitting atoms to shedding light on the building blocks of matter, this $3 billion international project shows how collaboration pushes science forward. The European spallation source opens new windows into the unseen, promising discoveries that could transform our lives. If you enjoyed exploring this incredible journey, please like and subscribe for more stories that unravel the wonders of engineering and science.